Hello, my name is Austin Venezia, and I'll be discussing Gram-Schmidt orthogonalization. So quick definition, the Gram-Schmidt process takes a linearly independent set S, which is equal to W1 all the way to WK, for k less than or equal to n, and it generates an orthogonal set S prime equal to V1 all the way to Vk that spans the same k-dimensional subspace R of n as S. Well, one thing to note is that S prime is orthogonal, which means that S prime is also linearly independent, and this is because every orthogonal set is also a linearly independent set. With that, we can then say that the dimension of the span of S prime of k is also equal to the dimension of the span of S of k. And with that, we can then say that the span of S of k is equal to the span of S prime of k. So this process constructs an orthogonal set from a linearly independent set, which means that the vectors that we found, the orthogonal vectors that we find from this process, we can create an orthonormal set from them. And for a set of linearly independent vectors to be considered orthonormal, this can only happen if and only if for all I of j in each vector, each projection of vi onto vj is equal to 1 if I and j are equal to each other. And then if this is not the case, then this will equal to 0. The projection will equal to 0. So a quick theorem. This is theorem 6.4 out of the textbook in chapter 6.2. We let V be an inner product space and S equal to W1, W2 all the way to Wn be a linearly independent subset of V. We define S prime equal to V1, V2 all the way to Vn, where V1 is equal to W1 and Vk is equal to this formula here for 2 less than or equal to k, which is less than or equal to n. One thing we do at the beginning, we set V1 equal to W1, and this is because for this process we're trying to find vectors v1 and through vn by first taking the original vectors in the inner product space, which is w1 to wn, and make them orthonormal to the previous vectors in S. But because there's no previous vectors than w1, this is the reason why we set v1 equal to w1. And that is the first vector we find, v1. And that's the reason why also we start at 2 compared to 1 in the formula. So then for the second vector, we are given, so for v2, we take w2 and subtract it by the projection of w2 onto v1. And that is multiplied by the vector v1 that we had just found. And then we divide that by the length of v1. So v1, the length here in the bottom left-hand corner, and we square that, and that gives us an orthogonal vector v1. However, this is not a orthonormal vector yet. We need to normalize it for this process. So to do this, we divide it by the length of this orthogonal vector v2. So v2, what we just found here, divide that by the length of v2, and that gives us the orthonormal vector. And then we continue this process for the remaining members of the set. So all the way up to Wn, whatever that might be. Okay, so let's go over a quick example. This is just one I just thought off the top of my head. So suppose we're in R3 and we let A1 equal to 100, A2 equal to 203, and A3 equal to 456. We want to use Gram-Schmidt to first compute the orthogonal vectors v1 to v2 to v3, which we can then normalize to obtain an orthonormal set. One thing to note right off the bat, if you look at these three vectors, they are they're linearly independent of each other. So that's a telltale sign that we can apply Gram-Schmidt's theorem or Gram-Schmidt's orthogonalization. So what the first thing we do is set v1 equal to a1, and then we're going to make this orthonormal. Again, this is not orthonormal quite yet. We divide it by the length of v1, so v1 prime, I guess you could call it, but in this case, since a1 is equal to v1, we divide it by 1, since the length is equal to the square root of 1 times 1. And hence our orthonormal vector is v1. Now we head on to v2. This is where we use the formula. So A2 subtracted by the projection of A2 onto V1 times V1, and divide that by the length of V1 that we found previously, squared. When we do that, so this is 203, this is A2, subtracted by 2, since this is the mapping from 2 onto V1, 2 times 100, and divide that by 1, since that is what we found in the first one. And we then discover that that is equal to 0, 0, 3. To make that orthonormal, we take the length of that, we divide it by this orthogonal vector here, and that gives us the orthonormal vector 0, 0, 1. And then we repeat the process again for V3, but we do add another, we consider another part of it. So V3 is equal to A3 minus the mapping of A3 onto V1 over the length of V1 squared times V1, and subtract that by A3 mapped onto V2, multiplied that by V2 that we just found, and that is divided by the length of V2 squared. There's a typo there, but that should be squared. And we find that out to be 456 minus 4 times V1, 6 times V2. And we find that this is also 1. If we were to take the length of this is going to be 1. And then that gives us 0, 5, 0. So this is orthogonal vector here. And then we make it orthonormal by dividing the length there again to give us 0, 1, 0. And so the orthonormal set is equal to 1, 0, 0, 0, 0, 1, and 0, 1, 0. And this holds true to the definition for orthonormal set. And that is that. Thank you.